When a new user signs up for an application, that application usually creates a new account for them and sends a welcome email. But sending emails is notoriously slow. Response time, however, is crucial for a great user experience. Nobody likes to wait. But when the actual account creation has succeeded or failed, we can yield that result to the user, even if sending the welcome email hasn't finished yet. We can run the slow task of sending emails outside of our main request-response cycle by offloading it into a background job. But background jobs can do much more than just improving response times. So today, I'm going to talk about how to use background jobs to scale applications and how they can help us to keep our code base simple. I'm going to start with a brief introduction to background jobs, describe some of their features that help with scaling, and how to master the challenges of working with them in order to make the most out of these features. I'll explain how asynchronous techniques like background jobs can actually go hand in hand with a RESTful approach. And I'm going to show you how to work with background jobs at scale and how we're using them at Shopify to scale one of the largest running Rails applications. In the example of a user signing up, background jobs are used to decouple the user-facing request from the time-consuming task of sending a welcome email. Our application server can fork a worker process and offload the slow task to the worker. It shouldn't wait for the worker to finish sending that email. But on the other hand, fire and forget is not a great approach either. We would like the worker to communicate in case something goes wrong. We can facilitate that communication by placing a message queue between the two processes. Sender and receiver of messages can interact with that queue at different times, which makes that communication asynchronous. The message in our case is the slow task of sending that email, which is why our message queue is also often referred to as a task queue. The application server drops the message into the queue, and it does not have to wait for the worker to process it. It can immediately move on and return to the user, which is why our response time is improved. We can also have multiple workers, and these workers can live on different machines as long as they have access to that queue. A task queue works best if it comes along with the so-called broker, which is routing the messages and managing the workers. And this is basically what a background job backend is, a task queue along with some broker code. It encapsulates all the hard stuff, all the magic, which allows us to keep our code base simple and easy to maintain. Our code is not aware of being run asynchronously on the worker. So, background jobs improve the user experience by improving response times, but how do they help to scale? If our application server experiences a sudden spike, for example in image uploads, that is not going to hurt us if the actual image processing is happening as a background job. Due to the spike, our queue might grow, and it's going to take a little bit longer until all the images are processed. But the users can still upload more images as fast as usual. The speed of queuing more jobs is not constrained by the speed of processing them. Our task queue serves as a buffer between the application server and the worker process. We can also add more workers on the fly so that we are processing more jobs at the same time, speeding up the whole process of the image process. So in fact, we're going to process multiple jobs in parallel, and we can also use this approach if we are facing a very large task. By splitting up the large task into many subtasks and queuing those as individual background jobs, they can run on the different worker machines at the same time, which effectively parallelizes the processing of the overall task. But our code is again very simple because it's not aware of being run in parallel. All it needs to know is how to do one subtask at a time. Background job backends usually come with some kind of retry functionality. If the worker encounters any kind of error when processing a job, the job is requeued after a bit of time so that it's going to be retried later. If all attempts of running the job fail, the job is marked as failed and no longer retried. When a worker succeeds running a job, it confirms that to the queue because now it's safe to remove that job from the queue. But if the job is never confirmed, another worker can pick up that job from the queue and try it. Some of our background jobs are more urgent than others. Sending a welcome email probably should happen soon after the sign-up. But cleaning up some stale data can certainly wait until tonight. At Shopify, we have some background jobs that are closely related to the checkout experience of the customers. And that is more urgent than, for example, firing webhooks to some third-party partners. A common feature of a number of background job backends is to allow for setting up multiple named queues and starting the workers with a queue list that is sorted by priority. Jobs queued into the high priority queue are going to be processed first. But if this queue is empty, the workers do not idle, but they are going to work on some jobs of lower priority. This feature also allows us to set up a specialized pool of workers that are only processing certain tasks. This is nice if some of our background jobs have special requirements, for example, need to run on certain hardware. Leveraging all these features can pose some challenges. By offloading some of my task into a background job, we are also moving it outside of the main transaction. So we're losing consistency guarantees. The best we can hope for is eventual consistency. But even that is not guaranteed. We might end up with inconsistent data if our background job fails. This is a general trade-off that we're facing here, that we need to balance the benefits of running something in the background against the risk of having some inconsistent state. However, we can try to contain the impact of inconsistencies, for example, by setting up some data reconciliation, maybe a scheduled background job that tries to find those inconsistencies and fixes them, or at least reports them. The job that is queued first is not necessarily the job that is processed first. Jobs leave the queue in a predefined order. But if we have more than one worker, we never know in advance which worker is going to work faster. Also, a job might face some kind of error. Then it's going to be re-queued, and retry it again later. So we cannot rely on the order of our background jobs. If the background job is used to build some kind of history or timeline, the order of jobs is not something we can rely on. So we should use, for example, an updated at timestamp or any other kind of timestamp that we have. If a background job depends on a different background job having finished, queuing both of them in the first place can also get us in trouble. Again, we cannot know which one is going to finish first. But if we are only queuing the first job, and after doing its tasks, this job queues the second job as a follow-up, we are on the safe side. We are making sure both jobs are running sequentially. If a worker does not confirm that the job was processed successfully in a certain time frame, we can allow another worker to pick up that job from the queue. But if the first worker didn't actually crash but was just a little slower than expected, our job ends up running twice. If we do not allow a second worker to pick up the unconfirmed job, we are running the risk of that job not running at all. So we need to choose between at least once and at most once delivery. At most once delivery is the right choice if running the job twice results in some problematic outcome that is worse than not running it at all. But more often than not, that points to a flaw in how the job is written. If the job is written idempotent, running it twice does not hurt at all and allows us to opt for at least once delivery, which ensures that the job is run. In many cases, idempotency comes basically for free. If we are removing some stale data or writing a default value into an empty column, this is already idempotent even if we don't think about it. In other cases, we need to pay a bit more attention. If the job is looping over all users and sending them an email, or even worse, charging them, running that twice will send the email twice or charge the customer twice. So in this case, we should carefully track whenever an email was sent or a customer was charged. And when the background job goes through that loop, it should check this state to learn if this record has already been processed by a previous run of the job. Background jobs don't have to be as fast as user-facing requests, but long-running jobs block our workers and prevent deployments, resulting in different workers running different revisions of our code base, which is not desirable. Now, if a user-facing request is too slow, we can offload some of the slow tasks into a background job. If a background job is too slow, we can basically do the same and offload some of its tasks into other background jobs. Either we split up the task into multiple jobs in the first place, or the background job that we queue can queue some follow-up jobs. So that might not reduce our overall processing time, but it is reducing the processing time of the individual job, which is what we care about here. Asynchronous techniques like background jobs require some extra care when exposing a REST API. If a post request offloads the resource creation into a background job, the status code 201 created is no longer appropriate. The resource has not been created yet. The creation can still fail, and we don't have the location of the new resource, so we cannot return it to the caller. Status code 202 tells a caller that the request was accepted, that it looks good so far, but it has not been processed yet. This can also return a location that points to a temporary resource, which is usually some kind of status monitor. The caller can poll this monitor in order to learn about progress for the resource creation. And when the server has created the actual resource, a request to the status monitor can return a 303 see other status code. And that comes along with the location of the new, freshly created resource. Now, in this case, the target resource that the caller requested is the status monitor. But what the caller gets is the new resource. This is not only a different representation, it's an entirely different resource, and this is the main difference between a see other and a regular redirect. A caller can also use the expect header in order to force synchronous or asynchronous behavior. A caller that sets the expect header to a 202 status code only is only willing to have the resource creation done asynchronously. While a caller asking for 200, 201, 204 enforces a synchronous resource creation. If the server is not able or willing to fulfill that, it can return expectation failed 417 status code. Background jobs provide benefits for applications of different sizes. For a small or medium-sized application, delayed job is a great starting point. Delayed job was extracted from Shopify and open sourced many, many years ago. And it's really nice to get started with if you are on Rails. You do not need any additional new infrastructure because delayed job persists the task queue using active record. So it ends up in the database that you are already using. The application should not talk to delayed job directly, but use active job that comes with Rails. Because active job is an abstraction layer that makes it very easy to replace the background job backend. If the application ever outgrows delayed job, it can be swapped so that a different background job backend is used without having to rewrite any code, because active job is handling that for us. Now, if the site is overloaded, the queue backs up a lot, the overhead of a relational database certainly makes that worse. Also with delayed jobs, the workers are mostly monitored from the outside. If something goes wrong, the worker is bloated, consumes too much memory, then all we can do is kill it and restart it. But restarting it is quite a pain because it reloads the whole environment, which means it reloads all of Rails. And we need to do those restarts pretty often, since that is basically the only way to deal with workers that are in trouble. Also, it's pretty hard to keep track of what's going on with all these workers because this killing and restarting happens from the outside. And this is where rescue is doing a bit better. rescue is using Redis to persist the task queue. Redis is known as a data store, but it actually has quite a number of features that are necessary for building great message queues. So by using Redis to persist the queue, the rescue Ruby code can focus on the worker problems. And it assumes from the very beginning that workers will get into trouble. They might lock up, run too long, have memory growth, and so on. So rescue does not run the background jobs in the worker process directly, but the worker forks a child process for every job. If something goes wrong, the worker can kill that child process, but that means we hardly ever have to restart the worker itself. Big advantage compared to delayed job. It's also much easier to keep track of what is going on. The worker is managing the state of all its childs, so it knows when it's killing one, when it's starting a new one, and so on. So Shopify Core is currently using rescue at a pretty massive scale. We are queuing tens of thousands of jobs per second, and rescue keeps up with that. However, forking all these child processes comes at a cost. So it is really memory-hungry approach, and speed is also not that great with rescue. Sidekick is doing a little bit better here. Sidekick is fully rescue compatible. So a job that rescue queues can be processed by Sidekick. And Sidekick does not fork child processes. Sidekick workers use threads for running the background jobs. And that means it's an order of magnitude faster and way less memory hungry. But unfortunately, it also means that all the code and all its dependencies have to be thread safe. Given the amount of data that Shopify is handling, there was basically no way around sharding the database. And the approach we have chosen is to not only shard the database, but set up what we call a pod internally, which is a database shard that comes with its own Redis, its own workers, and its own application servers. So we're hooking into Rescue's startup process and overwriting quite a bit of its code in order to make Rescue aware of this podded and sharded infrastructure. But having a background job system in place that understands that infrastructure makes it pretty easy to work with that system. Our database migrations do not run on deployment. We have a scheduled job that checks for pending migrations, write them into a database from where other scheduled jobs can work them off. And that keeps our deployments pretty fast and way less risky. But of course, it requires our code to work before and after running a migration. Most of our database migrations aren't even regular Rails migrations. The logs from an alter table in MySQL would just kill us. But in the end, even these migrations are run as background jobs. We also need to update large data sets on a regular basis. For example, when adding a new column to a database table, we might have to backfill it with data for existing records. We write a regular Rails database migration for that does not do any schema changes, but queues a background job doing the update of the data set. This means, since it is a database migration, our background job is queued after deployment. And we're even using this approach if we are only updating a smaller set of data. because it means that our updates are essentially just code changes, and we can treat them as code changes. They go through our regular quality assurance measures like code reviews. They are tracked in Git, which is really helpful when it comes to debugging. Backfilling a new column often means to iterate over millions and millions of records. So this basically results in a very long-running background job. If we want to shut down the worker, for example, for deployment, rescue makes us wait until the job finishes, effectively preventing deployments for this worker. Since we're deploying rather often, we would be running quite a number of different revisions at the same time, certainly not a desirable state. Sidekick is doing a little bit better than rescue, since it aborts a running job and requeues it if you want to shut down the worker. But even that would not necessarily be good enough for us. If the job starts from scratch every time it's retried, chances are it's getting aborted again before reaching the finishing line. If we are deploying faster than the job finishes, this job will never run. And our solution to that problem is our own abstraction layer for iterating over large collections. We're splitting up the job into two parts: the collection that is iterated over and the task to be done. The iteration can be done per record or in batches. And after each iteration, a checkpoint is set and the job is requeued. Next time it's picked up by a worker, it's starting from that checkpoint. This basically gives us interruptible jobs with automatic resuming. First of all, it allows for frequent deployments. For shutting down a worker, we do not have to wait until the whole collection has been processed. We only have to wait until one iteration has finished. But this approach also helps us with disaster prevention. For example, if our database experiences problems, we can throttle the running job or back it off completely, preventing it from making an ongoing incident worse or causing one in the first place. Also, if we need to move around data, the interruptible job helps us to preserve data integrity because we can fully automate everything without having to worry about our sharded and podded infrastructure. Controlling the iterations makes it easier to implement a progress tracking for these massive jobs. And it also allows us to parallelize processing. We can run multiple iterations at the same time on different workers. Some of these benefits can be reached by simply splitting up the large job into multiple smaller ones. But that makes it harder to track the progress or success of the overall job. This is easier with our abstraction layer because a resume is not a retry. So we can still observe retries and failures for the whole long-running big task. We're also encapsulating everything into this additional layer, which means we are hiding the scaling issues from the developers writing the background jobs. And this helps us to keep the code base very simple. Background jobs are easy to get started with, so even small applications can benefit, for example, from improving response times. But they require us to make some trade-offs, for example, around data consistency or delivery guarantees. But in the end, they help us to keep our code base simple, even if we're working at a massive scale. Thank you so much. If you have questions or comments, this is my Twitter handle. I'll also be around for the rest of the weekend. And if you would like to work on a system that queues tens of thousands of jobs per second and processes them, come and talk to me after. Shopify is hiring. Thank you so much.